Welcome. So today, we're basically putting on our detective hats and becoming mathematical investigators. Our case? Second-order differential equations. And the big mystery we're trying to crack is this. When you find a solution, how do you really know you found a complete solution? Let's get our toolkit ready.
So here's our game plan. We'll start by figuring out what the problem even is. Then we'll introduce our key tools, the fundamental set, the Wronskian, and this neat little shortcut called Abel's theorem. And then we'll put it all to work and close some cases with a few examples.
Okay, so let's start with this central mystery. Imagine you've been working on a problem, and you find two different solutions to a differential equation. That feels great, right? But are you actually done? Have you found every possible solution, or are there more hiding in the shadows?
And that leads us to the real question we're trying to answer today. What does complete even mean here? Well, a complete solution is one that's flexible enough, powerful enough to describe what the system is doing no matter where it starts. It has to be able to handle any initial conditions you could possibly throw at it.
So, to make our investigation a bit more official, mathematicians have given us our first big clue. It's a concept called a fundamental set of solutions.
And here's the formal definition. Basically, a couple of solutions, y1 and y2, form a fundamental set if you can mix and match them, c1 times y1 plus c2 times y2, to fit any starting point imaginable. This is the gold standard we're aiming for. This is what it means to say, yep, we found them all.
Okay, definitions are nice, but how do we, actually test if our solutions are up to snuff? We need a tool, a mathematical magnifying glass, if you will, to really inspect our solutions. And that amazing tool is called the Wronskian.
And the test couldn't be simpler. We have a fundamental set of solutions if and only if this thing called the Wronskian is not zero. If it's zero, it means our solutions are a bit too similar. They're stepping on each other's toes and can't cover all the possibilities. But if it's non-zero, we've cracked the case.
So how do we find this Wronskian? Well, it's just the determinant of this little 2x2 matrix. You pop your two solutions, y1 and y2, on the top row, then you put their derivatives right below them on the bottom row. Do a quick cross multiplication, y1 times y prime minus y2 times y prime, and boom, that's your Wronskian.
All right, let's add another tool to our belt. Calculating the Wronskian is super useful, but sometimes there's a faster way. Think of Abel's theorem as the expert investigator's secret weapon. It's a powerful shortcut that can save us a ton of time and effort.
Now check this out. Abel's theorem gives us a formula for the Wronskian using just the differential equation itself. And here's the really wild part. Notice how it only depends on that p of t term, the thing next to y. That means we can find out what the Wronskian is doing without even knowing what the solutions y1 and y2 are. How cool is that?
And this leads to something really useful. Think about it. That exponential part of the formula, e to the something, can never ever be zero. So that means the Wronskian only has two choices. It's either always zero or it's never zero. It can't be zero in one spot and non-zero somewhere else. Which means we only have to check its value at one single super easy point. What a time saver!
All right, theory's one thing, but an investigator is nothing without some fieldwork. Let's grab our new toolkit and actually put it to use. We're going to solve a few cases pulled straight from the study guide. Okay, case number 1. We've got two suspects, t and e to the t. First things first, we got to confirm they're actually solutions to the equation. A quick check, and yep, they are. Now let's hit them with the Wronskian test. The calculation gives us e to the t times t minus 1. Now, is this zero? Well, only if t equals 1. Everywhere else, it's not zero. So, do they form a fundamental set? Yes, they do. Case closed.
For our next case, we're going to use our shortcut, Abel's theorem. But hang on. Before you do anything else, look at step 1. This is so important, and it's probably the #1 mistake people make. Abel's theorem only works if the equation is in standard form, which means that y double prime term has to have a 1 in front of it. So we absolutely must divide the whole thing by 2t squared first. Once we do that, we can easily spot our p of t, plug it into the formula, solve the integral, and there's our Wronskian.
All right, time for the final case. This is the grand finale where it all comes together. We've got the equation, we've got two solutions, and we've got the initial conditions. That's the evidence for our case. Our job is to use our entire toolkit to find the one unique solution that fits all the facts.
So first, we run a Wronskian check to make sure we have a good foundation. We get x to the 6, which is definitely not 0, so great, we have a fundamental set. Next, we build our general solution. C1 times the first solution plus C2 times the second. Now we use our evidence, the initial conditions. Plugging in y of 1 equals 0 and y prime of 1 equals -1 gives us two simple equations. We solve for our constants, c1 and c2, and we find our culprits. The one and only solution that fits the evidence is y equals x to the third minus x to the fourth.
And just like that, you now have a complete investigator's toolkit. You know how to tell if a solution is complete. You know how to test for it with the Wronskian, and you know how to use Abel's theorem as a powerful shortcut. You can now take on any set of solutions and build the exact one you need for any situation. The only question left is, are you ready to go solve your own cases?